Okay, so we're going to get started on Chapter 2, Section 2. This section deals with conditionals and the related treatment of those. This is the section where some people have a hard time wrapping their heads around the concepts. They're not as intuitive as other aspects of logic. Let's get to the definition. If P and Q are statement variables, then the conditional of P by Q is if P then Q, or P implies Q, denoted by the right arrow pointing from the hypothesis, P, or antecedent, to Q, the conclusion or the consequent. The value of P implies Q is false when P is true and Q is false, otherwise it is true. So, where people can get a little mixed up is a conditional statement that is true by virtue of the fact that its hypothesis is false is often called vacuously true or true by default. So if P is false, then the overall statement is still true, regardless of what Q is. So if you consider the statement, if 0 equals 1, then 1 equals 2. 0 doesn't equal 1. So the overall statement is true. Because it is, like I said, as strange as it may seem, it is considered true, even though in this case both the hypothesis and conclusion are both false. But on the truth table, they are both true. Or they are true by default. The only time it is false is when the hypothesis is true and the conclusion is false. Okay, in expressions that include the conditional, as well as other logical operators, the order of operations is that the conditional is performed last. So, construct a truth table for the statement form P, if P or not Q, then not P. By order of operations, the following expressions are equivalent. You could add parentheses to make it more clear what means what. And then you fill in the 4 possible combinations for the truth values for P and Q. Then do the truth values for not P and not Q. Not P and not Q. From negation. And then P or not Q using the definition of or. So, hypothesis, conclusion, hypothesis implies inclusion is here. Which, if you want to look at the equivalence and the ability to reduce this statement, then this whole statement here is the equivalent to not P. because the truth values for all combinations match up between the whole statement and not P. All right. Logical equivalences involving the conditional. Again, the slides get kind of screwy on this program here. Use truth tables to show the logical equivalence of the statement forms. Yeah. Okay. Okay. But this one? Oh, okay. How do you arrive at the results of the last column? Use the rules for the implies, the conditional, to evaluate from the hypothesis and the conclusion. If the hypothesis is true and the conclusion is false, then the implication is false. Likewise here, if the hypothesis is true and the conclusion is false, then it's false. If the hypothesis is false, it's automatically going to be true regardless of what the conclusion is. If the hypothesis is true and the conclusion is true, then the implication is true. So again, this guy kind of got screwed up by the program running the PowerPoint presentation. Use equivalence to use tables to show the logical equivalence of the statement P or Q implies R, and P implies R, and Q implies R. All right. So first you fill in the 8 possible combinations of truth values for the variables. Then each component element of the statement, you do a column. And then for each of the 2 statements, the P or Q, P or Q implies R, P implies R, Q implies R, and then the and of the 2. So you create this monster table here. Huh? All right. So it can get to be a large table depending on how the complexity of the logical statement that you're trying to analyze here. But you can see that the first statement and the second statement have matching truth values for all combinations of the inputs. Now, representation of if-then as an or. Rewrite the following statement in if-then form. Either you get to work on time or you're fired. If you are not on time, then you are fired. Right? Yeah, kind of common sense. Remember that when you're running late for work? That's not necessarily true. You could be fired for another reason. So that's not the equivalent statement. So let not P be you get to work on time, and Q be you're fired. Then the given statement is not P or Q. Also, P is you do not get to work on time. So the equivalent of if-then version P implies Q. If you do not get to work on time, then you are fired. The negation of a conditional statement. All right. By definition, P implies Q is false if and only if its hypothesis P is true and its conclusion Q is false. It follows then that the negation of if P then Q is logically equivalent to P and not Q. This can be stated as this expression here. They are equivalent. So if you run into this, you can substitute it for this statement here, and vice versa. To attain this result, you can also start from the logical equivalence of not P or Q. Take the negation of both sides to obtain not P is, or not P implies Q is the equivalent to not P or Q negated. To Morgan's law, you get this expression, and then finally by the double negative law, you end up with P and not Q. So that would be the equivalent of the negation. Write negations for each of the following statements. If my car is in the repair shop, then I cannot get to class. If my car is in the shop, then I can get to class. And my car is in the shop, and I cannot get, and I can get to class. It's the opposite of the. If Sarah lives in Athens, then she lives in Greece. Sarah lives in Athens, and she does not live in Greece. She might live in Athens, Georgia. So car's in the repair shop, and I can get to class. So you change the if-then to an and then negate the second argument. Again, change the conditional to an and then negate the second argument. So the contrapositive of a conditional statement. Big word, basically just means flipping everything around. It's equivalent between this. It is the statement that if P, then Q, then if not Q, then not P. Flip them around and negate them both. That's the contrapositive. They are the contrapositive and the original statement are logically equivalent to each other. They can be substituted for each other. So it's just another way of expressing it. You can use these two examples. If Howard can swim across the lake, then Howard can swim to the island. Makes sense because the island isn't all the way across the lake. If you can swim all the way across the lake, then you can obviously get to the island. The contrapositive is if Howard cannot swim to the island, negate the second implies that he cannot swim across the lake. He can't even make it to the island. He obviously can't make it to the other side of the lake. Intuitively, it makes sense. If today is Easter, then tomorrow is Monday. If tomorrow isn't Monday, then today isn't Easter. Because Easter is always on a Sunday. So, there you go. Come on. So, there's the solutions. Converse and inverse of a conditional statement. The converse is flipping the variables, the statements around. If P then Q, the converse is if Q then P. The inverse is just inverting the two arguments, not switching them. So if P, not P, then not Q is the inverse of P implies Q. Note that these two are not logical or logically equivalent to the original statement. They are different. So if the converse and inverse, the converse of the Howard can swim across the lake, then Howard can swim to the island. The converse would be if Howard can swim to the island, then Howard can swim across the lake, which isn't necessarily true. The inverse, if Howard can't swim across the lake, then Howard can't swim to the island. Again, not necessarily true. Swimming to the island is a less distance, so he might be able to do that, but not swim across the entire lake. The same is true with the converse and inverse of the second statement. Converse would be if tomorrow is Monday, then today is Easter. Not necessarily. And then if today is not Easter, then tomorrow isn't Monday. Again, not necessarily true. So, there you go, the converse and inverse of each of those statements. A conditional statement and its converse are not logically equivalent. The conditional statement and its inverse are not logically equivalent. However, the converse and the inverse of a conditional statement are logically equivalent to each other. So if you run into one form, you can turn it into the other form and still maintain the logical validity of the statement. Now, the only if and the biconditional. Okay. Got another screwed up slide here. P only if Q means if not Q, then not P. This should read not if not Q, then not P. That let's see, this is not, it's a screwed up slide. Even publishers make typos. So rewrite the following statement in if-then form in two ways, one of which is the contrapositive of the other. Okay. First, the contrapositive. Invert the statements and switch them around, right? So if John does not run the mile in under 4 minutes, John will not break the world's record for the mile. Okay. What's the other one? Yeah, if he breaks the world's record, then he will have run the mile in under 4 minutes. That's the contrapositive, and then that's just another way of expressing the same sentiment. Definition of the biconditional. Given statement variables P and Q, the biconditional of P and Q is P if and only if Q, and is denoted by the double arrow. It is true if both P and Q have the same truth values, and is false if P and Q have opposite truth values. The words if and only if are sometimes abbreviated IFF. So, you are given this truth table for the biconditional. Now, I'm going to share with you something that they don't mention in digital logic. I forget how many people have not taken digital logic. So, oh, okay, more than I was thinking. Okay, for those of you that have taken digital logic, you will still not recognize this symbol. It's here. Probably should. Oops. It's an exclusive NOR gate. It's an exclusive NOR gate. I shouldn't be using my keys on the screen, but it's a gate to determine equivalence between two signals. It has the same truth table. If both of them are the same, it's true. If they're different, they're false. Even if they're both false, they're true. So if in digital logic you want to compare two binary numbers, just compare each corresponding bit using an XNOR gate, and if all the XNOR gates yield true or high, then the two numbers are equivalent, regardless of what the numbers are. So it's a faster way to do it than subtracting one from the other and then determining whether or not the result is 0. That's the other way of determining equivalence of two binary numbers. But yeah, that's the XNOR gate. It is the circuit equivalent of this setup here. Okay, the order of operations of the biconditional is co-equal with the conditional. The only way to indicate precedence between them is to use parentheses. The full hierarchy of operations for the 5 logical operators is below. First you do negations, then you do ands and ors, then you do your conditionals. All right. Rewrite the following statement as a conjunction of 2 if-then statements. This computer program is correct if and only if it produces correct answers for all possible sets of input data. So it would be if the computer program is correct, it produces correct answers for all possible sets of input data. And if the computer program produces correct answers for all possible sets of input data, then the computer program is correct. Goes both ways. So it's like saying this P implies Q and Q implies P. So that's why the arrows face both directions. They both imply each other. So that's what I said. Yeah. So necessary and sufficient conditions. R is a sufficient condition for S means if R then S. A necessary condition for S means that if not R, then not S. So if R is true, then S is true. R is a sufficient condition for S. If R is not true, then S is not true. That means R is a necessary condition for S. This is the inverse of this, right? The inverse, they are not necessarily the same. So write this statement in the form of if A, then B. Pia's birth on U.S. soil is a sufficient condition for her to be a U.S. citizen. If Pia was born on U.S. soil, then she is a U.S. citizen. So there you go. Use the contrapositive to rewrite the following statement. George's attaining age 35 is a necessary condition for his being president of the United States. Contrapositive. Invert and reverse. Well, if George is not age 35, then he is unable to become president of the United States. What was the other one? If George is not, and if George can be president of the United States, then he has attained the age of 35. So this is the contrapositive of this one. So, and because the contrapositive is the equivalent of the original statement, they're both true. Okay, that's it for conditionals. You'll move on to come on. Been a bit glitchy today. All right. Valid and invalid arguments. Stringing together logical statements to create an argument that will hopefully be true or whatever you're trying to express. An argument is a sequence of statements. All statements in an argument, except for the final one, are called premises, or assumptions, or hypotheses. The final statement is called the conclusion. The symbol 3 dots here, which is read therefore, is normally placed just before the conclusion. To say that an argument form is valid means that no matter what particular statements are substituted for the statement variables in its premises, if the resulting premises are all true, then the conclusion is also true. To say that an argument is valid means that its form is valid. So what does all that mean? Well, testing an argument form for validity. Identify the premises and conclusion of the argument form. Construct a truth table for showing the truth values for all the premises and the conclusion. A row of the truth table in which all the premises are true is called a critical row. If all the premises are not true, it is not relevant, so you can ignore those. If there is a critical row in which the conclusion is false, then it is possible for an argument of the given form to have true premises and a false conclusion, and so the argument is invalid. If the conclusion in every critical row is true, then the argument form is valid. So if all the premises are true and all the conclusions are true, then the argument is valid. So, let's see here. Determine whether the following argument form is valid or invalid by drawing a truth table. All right. When you fill in the table, you only need to indicate the truth values for the conclusion in the rows where all the premises are true. So, determine the truth values for this one. Determine the truth values for this one. And this one. And if both of these are true and this is true for all conditions, or for all conditions where these are true, this is true, then the argument is valid. Okay? So, we'll skip the explanation and look at it graphically. So, only in these two columns are you worried about for the premises. You don't have to worry about all this. That's just building this. If both premises are true, that's a critical row. So there's 4 critical rows. Now, the conclusion for those critical rows, are they all true? No. So it is an invalid argument. A judge would throw it out in court because it could be false. Has to be true for all cases. Modus ponens and modus tollens. I forget my Latin, so I don't remember exactly the translation for those. But that is Latin. I do remember that much. I should look that up before our next class. Anyway, an argument of form consisting of 2 premises and a conclusion is called a syllogism, or something like that. Syllogism. And the first and second premises are called the major and minor premises, respectively. And the most famous form of the syllogism in logic is called modus ponens. It has the following form. P implies Q. P is true, therefore Q is true. Pretty simple, yeah. Therefore. Yeah, it's just saying this is the end of the argument. So, if P implies Q, and P is true, then Q is true. Pretty intuitively, you should be able to follow that. And They skipped the slide. They didn't explain what modus tollens is. I'll get to that in just a second. Here's an argument of this form. If the sum of the digits of this number is divisible by 3, then this number is divisible by 3. The sum of the digits is divisible by 3. Therefore, this number is divisible by 3. Pretty simple logic. That's modus ponens. They skipped the slide on modus tollens. We'll get to that in just a minute here. Fill in the blanks. Following arguments slowly become valid inferences. If there are more pigeons than there are pigeonholes, then at least 2 pigeons roost in the same hole. That's the first statement. There are more pigeons than there are pigeonholes. Therefore, at least 2 pigeons roost in the same hole. Pretty simple logic. Now, modus tollens is kind of the opposite. If this number is divisible by 6, then it is divisible by 3. If P, then Q, this number is not divisible by 3, not Q, therefore not P. So this number is not divisible by 6. That's modus tollens. If P then Q and not Q, then not P. Okay? Like I said, it's not, they didn't express that on the slide. Not yet. So at least 2 pigeons roost in the same hole, and that number is not divisible by 6. Additional valid argument forms. Various rules of inference. All right. A rule of inference is a form of argument that is valid. Modus ponens and modus tollens are both rules of inference. Some more examples of rules of inference are to follow. All right. Generalization. If P is true, then P or Q is also true. You can add to it. You can make a more general statement. If Q is true, then P or Q is also true. So that's generalization. Take the example of you ask a classmate what class he's in. He said, and they're told he's a junior. Therefore, Anton is either a junior or a senior, an upperclassman, which is one of the two. So you can make generalizations using this rule of inference. Specialization has to do with the AND operation. If P then and Q is true, therefore P has to be true. Because if the AND operation is true, then both of its individual statements are also have to be true, right? So P and Q, therefore Q, and therefore P. So that's for specializing. And give an example. Looking for a person who knows graph algorithms. Anna knows both numerical analysis and graph algorithms. Therefore, in particular, Anna knows graph algorithms, which is all that you're looking for in general. So With the and, you can if an and operation is true, you know that both of the statements are also true. The following statements are also true. If P or Q and not Q, therefore P is true. If P or Q is true, one of them has to be true. But Q is not true, therefore P has to be true. Right? Okay? So, in the, for a particular number x, positive number x minus 3 equals 0, or x plus 2 equals 0. Now, we also know that x is not a negative number. Therefore, x plus 2 is not equal to 2, or x plus 2 is not equal to 0. By elimination, you can conclude that x minus 3 must equal 0. So, the following argument is valid. Transitivity. P implies Q, Q implies R, therefore P implies R. This is, you can have long strings of if-then statements and chains of them, and one implies the next and the next and the next. You can conclude that the first statement implies the last statement. So, in the example below, suppose n is a particular integer. If n is divisible by 18, then n is divisible by 9. If n is divisible by 9, then the sum of the digits of n is divisible by 9. Therefore, if n is divisible by 18, then the sum of the digits of n is divisible by 9. If this is true and this is true, then this is true. By transitivity. This argument form is valid. Proof by division into cases. P or Q is true. P implies R. Q implies R. Therefore, R is true. So, for P or Q to be true, one or the other has to be true. If P is true, P implies R, then R is true. If Q is true, Q implies R, therefore R is Q. True. So, you can, with the OR statements, if both sides of the OR statement imply the same thing, then that thing must be true. Give it a little example. You know that x is positive or x is negative. You can deduce that x squared is greater than 0 by arguing as follows. X is positive or x is negative. If x is positive, then x squared is greater than 0. If x is negative, then x squared is also greater than 0. Therefore, x squared is greater than 0, assuming x is either positive or negative, and not 0. Okay, here's a little bit more complex of a problem. You don't have your glasses when you get to class. You know these things are true. If I was reading my class notes in the kitchen, then my glasses are on the kitchen table. If my glasses are on the kitchen table, then I saw them at breakfast. I did not see them at breakfast. I was reading my class notes either in the living room or in the kitchen. If I was reading my class notes in the living room, then my glasses are on the coffee table. So where are the glasses? On the coffee table. Let's break it down formally. Let RK and GK and SB and RL and GC mean those basic statements that we accepted before. Sequence of steps that you could use to reach the answer, which we did intuitively pretty quickly. If I was reading in the kitchen, then the glasses are on the kitchen counter. Okay, that's by the statement given earlier. And if the statement from the statement earlier, if the glasses are on the kitchen table, you saw them at breakfast. Therefore, if I was reading in the kitchen, then you would see them at breakfast because of transitivity. Take that conclusion and then see that you did not see them at breakfast. So the glasses you were not reading in the kitchen by modus tollens. The last, the statement D in the original problem means it says that you were either reading in the living room or reading in the kitchen. You weren't reading in the kitchen by the conclusion of the previous section. Therefore, you must have been reading in the living room by elimination. You were reading in the living room implies that the glasses are on the coffee table. You were reading in the living room, therefore, by modus ponens, the glasses are on the coffee table. Now we get to fallacies. A fallacy is an error in reasoning that results in an invalid argument. Three common fallacies are using ambiguous premises and treating them as if they were unambiguous. Circular reasoning, assuming that what is proved, assuming what is to be proved without having derived it from the premises, and jumping to a conclusion without adequate grounds. Two other fallacies, converse error and inverse error. They superficially resemble those valid arguments by modus ponens and modus tollens, but they are not, in fact, valid. So watch out for these. We can show that an argument is invalid by constructing a truth table and finding at least one critical row in which all the premises are true, but the conclusion is false. That was what we covered earlier. Another way is to find an argument of the same form with true premises and a false conclusion. We went over this earlier. Argument to be valid, every argument of the same form whose premises are true, all true, must have a true conclusion. It follows that for an argument to be invalid means that there is an argument of that form whose premises are all true and whose conclusion is false. The converse error. The converse is not the same as the original statement. So, If Zeke is a cheater, then Zeke sits in the back row. Zeke sits in the back row, so Zeke is a cheater. We know intuitively that it's not a valid argument. Not all people that sit in the back row, including Zeke, are cheaters. Are you? People in the back row? Cheaters? No? Okay. Just checking. But this looks like a modus ponens type of thing, but it's not, because it's the second argument is presented in the second line. I mean, the second statement is presented in the second line. Yeah, the second statement is in the second line rather than the first one. It's not biconditional, so it doesn't imply the other direction. There's an exercise that you're asked to use a truth table to show the form of that this form of argument is invalid. Inverse error. If these two vertices are adjacent, then they do not have the same color. These two vertices are not adjacent, therefore these two vertices have the same color. Looks like modus tollens, but it's not. It's the inverse of the first statement, not the second statement. So it is not a valid argument. It is like trying to say not P implies not Q, which is not the case. That's the inverse. The inverse is not the equivalent to the original statement. Okay. The argument is valid by modus ponens, but its major premise is false, therefore its conclusion is false. If Canada is north of the United States, then temperatures in Canada never rise above freezing. Canada is north of the United States, using modus ponens, therefore temperatures in Canada never rise above freezing. Well, this is false, so the conclusion is false. So it's a valid argument form, but a false premise can give a false conclusion. This is an invalid argument with true premises and a true conclusion, just by coincidence. If New York is a big city, then New York has tall buildings. New York has tall buildings, therefore New York is a big city. Not necessarily true. If you substitute Jackson for that, if Jackson is a big city, then Jackson has tall buildings. Jackson does have tall buildings, but is Jackson a big city? Not by most people's standards. Not compared to Chicago, Dallas, New York, Miami. But Jackson does have a tall building or two. So the argument is invalid by converse error. So Let's see here. An argument is called sound if and only if it is valid and all its premises are true. An argument is not sound is called unsound. Kind of a gimme there. The important thing to note is that the validity is a property of argument forms. If an argument is valid, then so is every other argument that has the same form. Similarly, if an argument is invalid, then so is every other argument that has the same form. Contradictions and valid arguments. The contradiction rule. If you can show that the supposition that the statement P is false leads logically to a contradiction, then you can conclude that P is true. So, if you assume P is false and your argument leads to a contradiction, then you can conclude that P is actually true instead. So, show that the following argument form is valid, where not P implies C, where C is a contradiction. P implies C, therefore P. Prove the contradiction rule. So do a truth table. The only critical row is the row that has not P implies C as true. P is also true. From way over there. So if the premise is true, if this is true, then P is true. So you can assume that a statement is false. If that implies a contradiction, then the statement is in fact true. So, this fellow here describes an island containing two types of people, knights and knaves. Knights always tell the truth and knaves always lie. You visit the island and are approached by two natives who speak to you as follows. B is a knight. B says, A and I are of opposite type. What are A and B? Knights, one of each. Both knights, both knaves. I'm sorry? Oh, okay. So, what are A and B? Mm-mm.
He's a knight.
Mm-mm. They are both knaves. They are both knaves. Huh? Knaves lie, so they're not of opposite type. Mm. Yeah. Okay, you see it now? So suppose A is a knight. Okay. What A says is true. Therefore, B is also a knight, because that's what A said. Because a definition of a knight, what B says is true. Therefore, A and B are of opposite types. That's what B said. We have arrived at the following contradiction. A and B are both knights. And A and B are of opposite type. Oops. Both are lying. The supposition is false. A is not a knight. A is a knave. What A says is false. And A said B is a knight. So B is not a knight, therefore B is also a knave. So the summary of rules of inference. Get your cameras out. This is the table that has the most important rules of inference. Modus ponens, modus tollens, generalization, specialization, conjunction, elimination, transitivity, proof by division into cases, and the contradiction rule. All right, and that will be about sum it up for the day, unless there are any questions.